All right, so here we go. Example 4, we're talking about Taylor polynomials. Remember, Taylor polynomials are used to approximate non-polynomial functions. And as we did see yesterday, they can also be used to approximate themselves perfectly, excellently. All right. So here's a typical question. Find the Taylor polynomial of degree 6, a 6-degree Taylor polynomial, for the function the natural log of x with c equals 1. That means the center of the approximation is 1. So we can't really center the natural log at 0. Why not? It doesn't exist there. But 1 is a really nice point, because what's the natural log of 1? 0, right? It's the x-intercept. So we know that. But the natural log of 1.3, not as easy to find. Then use that polynomial of degree 6 to approximate the value of natural log of 1.1. All right? So instead of using a tangent line or Euler's method, we're going to do it with a Taylor polynomial. So we need to get the numerators of the coefficients ready to go. This is what I called the machinery yesterday. So if the function is the natural log of x, and our c value is 1, again, that's pretty important, then what is f of c? What is f of 1? It's the natural log of 1, which is 0. So there's the numerator of our first term. F prime of x is 1 over x, and then f prime of 1 is 1 over 1, which is 1. The second derivative is, what's the derivative of 1 over x? You want to use the Hody-High rule? Negative 1 over x squared. Yeah, so I'm going to call it negative x to the negative second, which is negative 1 over x squared. And then f double prime of 1 is negative 1. All right, so we got to keep going pretty far because we need to get out to a degree 6. So leaving it in this power rule form is not bad. So that's going to be a positive 2 x to the negative third, which is 2 over x cubed. And then f triple prime of 1 then is going to be 2. The fourth derivative, so remember we switched to Arabic with parentheses, that's negative 6 x to the negative fourth. So you could just jump over here. The fourth derivative at 1 is negative 6. And then the fifth derivative, which is hopefully the last one, is 6 times 4. That's positive 24x to the negative fifth, which means the fifth derivative at 1 is positive 24. Oh, we got to go one more. I lost track. Sixth derivative. So now it's 24 times 5, which is negative 120, x to the negative 6. And then the sixth derivative there is negative 120. Do you notice a pattern in these numerators? First of all, they do what? Plus, minus, they alternate. That's interesting. It's factorial. Yeah, and it's a direct result of the power rule, right? We started with a 1, and then the power rule, then we multiplied by 2. And then on the next one, we took the 2 and multiplied by 3, and then for the 3, we multiplied by 4, 4 times 5, 5 times 6. So there is a factorial going on here. Yeah. Just for what it's worth, this would be 2 factorial. This would be negative 3 factorial. This would be 4 factorial, and this would be negative 5 factorial. Okay, and working backwards, this would be negative 1 factorial. And I guess this would be 0 factorial. Sweet. So you want to kind of notice patterns here. All right, so anyway, now that we have all of our numerators of our coefficients, we can finally set out to create the polynomial. So here we go. P sub 6, they gave us the name, of x is, and again, you can get the pattern going from the very beginning, but it's probably easier just to rely on your old habit of writing equations of tangent lines, because the first two terms don't really show the pattern. So it's the y value, which is 0, plus the slope, which was 1, times x minus the x value, which is the center of 1. So that would be the tangent line polynomial, the first degree Taylor polynomial. And so now the pattern picks up when we get to the second, the power of 2. So now the numerator is minus 1, and that's over 2 factorial times x minus 1 squared. The next numerator is positive 2 over 3 factorial times x minus 1 cubed. And then the next coefficient in the numerator is negative 6 over 4 factorial times x minus 1 to the 4th, so on and so forth. The next numerator is positive 24, all over 5 factorial times x minus 1 to the 5th. And then finally, the last term is negative 120 in the numerator. And we're on the 6th degree term, so it's over 6 factorial times x minus the center to the 6th power. So there's your 6th degree polynomial. And you could probably then generate subsequent terms by recognizing the pattern that's inherent in here, which is the factorial pattern for those numerators. Okay, so anyway, what do we know about this? What do we know about the polynomial at 1 and the actual function value at 1? What do we know about them? They should be what? The same. Good. And they are. You could verify by plugging a 1 into all those terms. So at the center of approximation, the function value and the polynomial that's approximating it are the exact same. But everywhere else to the left and right, it's only an approximation. Okay? So here we go. We say then, kind of like we did with Euler's method or tangent line approximation, the natural log of 1.1 is approximated by piece of 6 of 1.1, which is equal to. All right? So now let's just go ahead and plug it in. When you plug in your 1.1 for x, you subtract 1 right away, so you get 0.1. So it's going to be 0.1 minus 0.1, I'm going to throw these in the numerator, squared over 2 factorial, plus 2 times 0.1 cubed over 3 factorial, minus 6 times 0.1 to the 4th over 4 factorial, plus 24 times 0.1 to the 5th over 5 factorial, so on and so forth. And one more, minus 120 times 0.1 to the 6th, all over 6 factorial. So that's the exact answer. And again, if this were like a no calculator question, first of all, you wouldn't be asked to do so many terms. They usually ask you to do like a 2nd degree or a 3rd degree polynomial. If it were a calculator question, you could even leave it like this. But of course, at this point, if you want to see what it's actually equal to, you could type it in. Do you want to go through and do that? Sure? Okay, yeah. I'd be curious. So first of all, the natural log of 1.1 is this. And remember, we said your calculator computes that number by generating what we just did. It's programmed to do that. I don't know how many terms it goes to give you this level of accuracy, but this is how it does it. So let's compare. I'm just going to do it this way. I'm going to do 0.1, and I'm going to store that as x, just so I don't have to type so much. So now for me, it's x minus, and then x squared divided by 2 factorial is 2. Factorials are just extra keystrokes, plus 2 times my x cubed, and then divided by 3 factorial, which is 6. I don't want to bother with horizontal division bars either. Minus 6x to the 4th for me, divided by 4 factorial, which is what? Just multiply 6 times 4 is 24. And then plus, and you could probably even work this out to a simpler pattern if you simplified your factorials in your numerators. So now plus 24 in the numerator times x to the 5th divided by, there we go, divided by 5 factorial, which is what? 120. And then plus 120. No, it's minus 120. Sorry, that would make a huge difference. Minus 120 times my x to the 6th power, and then divided by 6 factorial. I'm just going to go ahead and write 6 factorial, just so I don't have to do that in my head. 6 times 120. And then you can compare it, and you got 0, 9, 5, 3, 1, 0, 1, and then it deviates. So 1, 2, 3, 4, 5, 6, 7. We are correct to 7 decimal places. Now notice that our answer is a little bit smaller. Our answer is a little bit smaller. So our curve is what? Above or below the actual? It's below. Yeah, it's below the actual. Okay. There you go. That's pretty good. So again, those are pretty tedious polynomial calculations, but They're still something that you can actually conquer back in the day before calculators. So obviously our calculator, when it computes the natural log of 1.1, it's programmed to go out past the 6-degree polynomial because it has different decimals than we do. Okay? All right. Excellent. Excellent. Fantastic. Wonderful stuff. Yeah. Cool. Any comments or questions on that one? Unless they say otherwise. Bless you. Yeah. This is one of those cases where they might say approximate it to 5 decimal places. Okay. But if they don't say that, yeah, then just 3 decimal places. Or an exact answer. Like that. Okay. Let's move on to number 5 then. Suppose that little g is a function which has continuous derivatives. Bless you. And g of 2 is 3, g prime of 2 is negative 4, g double prime of 2 is 7, g triple prime of 2 is negative 5. What did they just give us? They just gave us all the stuff that we usually have to toil over to find. They gave us the numerators of our terms. Sweet. Thank you. Write a Taylor polynomial of degree 3 for this unknown function g centered at 2. So this is a good way to test your knowledge of what a Taylor polynomial is. By the way, could we call this one a Maclaurin polynomial on example 4? No, because Maclaurin polynomials are always centered where? At 0, and this one wasn't. Okay, just to review. So anyway, where's this one centered at that they gave us? 2. Okay, so let's go ahead and write the Taylor polynomial degree 3. So let's call it t sub 3 of x. You could use p. You can even use f of x, but typically we call the function f that we're trying to approximate, but they named it g here, so if you wanted to call your polynomial f, that wouldn't be a bad deal. Just make sure you call it something different. All right, so the first term is going to be like we were writing the equation of a tangent line. It's the y value at 2, which is 3, plus the slope at 2, which is negative 4, times x minus the x value of 2. So if you kind of get that part out of the way, that's the Taylor form of the line. Now the pattern picks up. Now the second power term is going to be plus 7 over 2 factorial times x minus 2 squared. Don't forget to divide it by n factorial. And then we're on the third derivative, so it's negative 5 over 3 factorial times x minus 2 cubed. And that's it. Now, if you wanted to make it extra fancy, in front of t sub 3 of x, you could put g of x, and what would go between g of x and t of x? A squiggles. Excellent. This is kind of where they get picky on free response. When you're talking about polynomials and you're missing a squiggle, they tend to take off, okay? There you go. So that was it. So that wasn't too bad. You're handed the information. You just need to know what to do with it. The most common mistake students make is they forget to divide by n factorial. All right? So again, to create a polynomial, go ahead and write the equation of the tangent line like you're used to doing, and then the pattern kicks in. But of course, the pattern is still there. We already saw why that 0 factorial and 1 factorial don't need to be shown. Okay. That was a lot of space for that one. Didn't probably need that. Maybe draw something here just to kind of use the space. Yeah. Yes, I'm trying to make a grilled cheese. Oops, I meant to use this. It's a grilled cheese sandwich. So there's the cheese, and then it's always a good grilled cheese sandwich always has like, right? Yeah. And then put the grill marks on top. Oh, okay. Man, that's really oh, you want to draw some juice coming out? There you go. Happy National Grilled Cheese Sandwich Day. If that don't make you hungry, I understand why. Yeah. Yes. Mm-hmm. They would probably have the answers. The question was, if they actually had you approximate something at a certain value, and the answer choices were decimals, could you cheat and not go all the way out to the third step and find it by the first or second term only? Possibly, but they know that students might do that, so they might make it, all the answer choices might be so close in the first 2 or 3 decimals that you would have to go out far enough. Yeah, it wouldn't be like a 5 and a 7 and then 3.214, okay, or something like that. They would all be like 3.124, 3.125, and 7, whatever. It's only 4 answer choices now instead of 5. It's kind of nice. All right, example 6, use. Okay, so now we're using, instead of just generating, finally, a third-degree Taylor polynomial approximation of e to the x. Near 0, okay, in the vicinity of 0, to evaluate this limit, and then compare it to the actual limit. Is it surprising? Why or why not? Oh, I'm getting ahead of myself. All right. First of all, I need to generate a third-degree Taylor polynomial for e to the x. Near 0. What's the easiest value near 0 for which we know the exact value of e? 0. 0 is very near 0, right? What's e to the 0? 1. So that's what their way of saying center it near 0. Because remember what we're saying, in the vicinity of 0 then, e to the x is going to act very, very similar to its polynomial that we're about to generate. And they would have the exact same value at 0. So let's go ahead and center it at 0. And we'll go ahead and do our groundwork here. F of x equals e to the x. And f of 0 is e to the 0, which is 1. All right, f prime of x is e to the x. So f prime of 0 is going to be e to the 0, which is 1. F double prime of x is e to the x. And so f double prime of 0 is e. Yes, you can jump ahead. No, yeah. You're not going to necessarily get credit for this work here. That doesn't mean you want to slip on notation, because anytime you say something incorrectly, even though it's not what they're looking for, you'll lose points. So make sure you're still using correct notation there, not getting sloppy on a free response. But yeah, I think I could figure out what the numerators of all my coefficients are. 1, very good, said Gorell. Okay, so here we go. E to the x, Scowiggles. I like T for Texas. T for Taylor also, and it's a third degree, so the subscript is optional. You don't have to put that. But writing the equation of the tangent line is, first of all, the y value, which is 1, plus the slope, which is 1, times x minus the center. I'm just going to put x to the first. Are you okay with that? X minus 0, which is just x. So is this a Maclaurin polynomial? Yeah, it actually is. And then plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x minus 0, or just x, cubed. Now notice, if you had to generate more terms, this one simplifies down to something pretty darn easily, right? What would be the next term if we had to add one? Yeah. So this is one of the Taylor series in the next section that you're going to have to memorize. So hopefully you memorize as you go. Natural log would not be a bad one to memorize. I could have simplified these terms right here and distilled the better inherent pattern, but I didn't do that because you don't have to memorize that one. But e to the x, cosine x, sine of x, and then 1 over 1 minus x is another one you have to memorize. E to the x is pretty darn easy. It doesn't alternate, and all the terms are positive then, and it's just x to the n over n factorial. Okay? But anyway, here's a third degree polynomial. E to the x is approximated by that. And so now, here we go. We're using it. The limit as x goes to 0 of e to the x minus 1 over 2 to the x. Now, because we're approaching 0, and we centered our approximation of the polynomial, what happened at 0, we can substitute this in. So that's going to be approximated by the limit as x goes to 0 of. And let's go ahead and substitute this, copy it for e to the x in the limit. Boom. Okay? And then I have my minus 1 from the numerator all over 2x. All right? So I substituted this for that, which is okay. That's the whole idea behind, bless you, these things. They act the same way as the functions do in the neighborhood of the center. All right, so now if I do that, that's equal to, I only use the squiggle once. I don't have to keep putting squiggle. It's just when I make the transition from the substitution. Now the ones will cancel, right? And every term that's going to be left then is going to have a what in it? An x, which I can then factor out. And I'm left with 1 plus x over 2 factorial plus x squared over 3 factorial, all over 2x. And by the way, we already tried never not first direct substitution. We got 0 over 0. We could say we did, right? Yeah, sorry. And then the x's divide out. And now we can use direct substitution. So that equals 1 plus 0 over 2, so we get a half. Okay? So you'll see in the subsequent sections, we start using these polynomials not just to approximate the functions, but if I want to know what their derivative is, or if I want to know what their integral is. It's a lot easier to take integrals and derivatives of polynomials using power rules than it is for some functions that maybe you don't know what the derivative is. Okay? Not necessarily for sine, cosine, and e, but because they behave the same way, we could start manipulating them the same way we would the original function. All right, so let's actually find the true limit of this. The limit as x goes to 0 of e to the x minus 1 over 2x. If this were just a multiple choice question, you would plug in and get 0 over 0. And now we could use what rule here? L'Hopital rule. So let's lop it. Lop it. And we get the limit as x goes to 0. The derivative of the top is e to the x. The derivative of the bottom is true. Now you use direct substitution and you get what? 1/2. All right, so now the follow-up question. Is this surprising? It is? Is it cool? Is it awe-inspiring? Yes, yes, yes. But at this point, should it be surprising? Not really. Okay? Why? Or why not? You're going to make me say it. That's okay. E to the x and that third-degree polynomial in the neighborhood of 0 essentially are the same. Essentially. Not exactly. They are only the same at 0. But they are essentially the same in the neighborhood of 0. And how big is the neighborhood? Well, yeah, relatively big. If you have a cubic, you can go maybe relatively to the left and right by, maybe a whole unit or so. I don't know. If you add more terms, the neighborhood gets bigger, right? It's that radius that you can drift left and right of and still get good approximations. Okay, sweet, sweet, sweet. Last page, example 7. Oh, I like this type of question. These make fantastic, fantastic multiple choice questions. All right. Given that p sub 2 of x is a plus bx plus cx squared, is a second degree Taylor polynomial, just looking at it, you could guess it's centered where? At 0, okay? Because if it were centered somewhere else, you would see x plus or minus the center, x plus or minus the center. And it tells you it's centered at 0. What can you say about the signs of A, B, and C if the graph pictured at the right is the function f of x that it's representing? So f of x is approximated by this second degree polynomial, and here's the graph of f. What can you say about the sign of A, B, and C? A, B, C. Any idea? Well, let's see. It's written in increasing order. So normally we put A as the coefficient of x squared, don't we? Like in algebra 2. But that's when we write it in descending order. We generate terms by adding powers, so we are now writing them in ascending order. So the y-intercept of our polynomial is A. So remember, the polynomial and the function itself at 0 have the exact same value. F of 0 is equal to p sub 2 of 0. They are the exact same value. Everywhere else, they're only approximated. So what is the y-intercept of this function? It's positive. So I know that A is greater than 0. Sweet. Okay. Now, you could probably do C pretty easily. C is the coefficient of x squared. Do you think the polynomial that approximates this is going to open up? Or do you think it's going to open down? Just guessing. Yeah, our curve is concave down. So it's probably going to be best approximated with a polynomial that is opening down, right? Which means that the coefficient of the x squared term should be what? Negative. And it is. Yep. Now notice when I drew my quadratic, I didn't draw the vertex there. Because if I drew the vertex there, my radius on either side would not be symmetrical. So what's probably happening is the quadratic that approximates it maybe has a vertex right here at that x value. So remember, in any polynomial, the linear term is responsible for the horizontal shift. You know that because when you completed the square, that affected the horizontal shift. Can you tell if b is positive or negative based upon this? It looks like the graph would have to be shifted a little bit to the right. So does that mean b is going to be positive or negative? Negative? I'm not so sure about that one. So here's another way you can answer these questions the exact same way. Remember that when we generate these terms, a plus bx plus cx squared, let me rewrite it. A is equal to, because it's the constant, which is the function value, it's equal to the zeroth derivative at 0 over 0 factorial, right? The function value itself is the zeroth term. And b, the power on x to the first, is equal to f prime of 0 over 1 factorial. And c is equal to, it's the quadratic term, so it's equal to f double prime of 0 over 2 factorial, right? So knowing the formula for the coefficients, which again in general is this, it's the nth derivative at the center over n factorial. These are your coefficients. So here's the other way to do it. Notice that 0 factorial, 1 factorial, 2 factorial, they're all positive, right? Anything that's factorial for us is going to be positive. So the sign of a, b, and c is determined by the numerators. Yes, yes? Okay. Now f to the 0 power of 0, that's just the same thing as f of 0. So a is equal to f of 0, the sign of it. Okay, we'll say the sign. And then b's sign is equal to the sign of f prime of 0, and the sign of c then is equal to the sign of f double prime of 0. Well, when we translate it into that, we have now something that we've been training all year long to look for graphically. F of 0 is the y value there. F prime of 0 is the slope value there. And f double prime of 0 is the concavity there. So that makes it almost easier to answer. So for A, yeah, the y value is a positive number. Boom. For C, the curvature is negative. Our graph of F is concave down, so that is less than 0. But what about B? What's the slope of this graph there? Positive. So guess what B is? It's actually not less than 0. It's greater than 0. And now we know definitively. So this part right here can be asked in so many different ways. If you know how to generate the coefficients of a polynomial using Taylor's rule, you can always compare that expression to the coefficient in a given polynomial. Okay? And then you can solve or figure it out. And that happens a lot of the times. Okay? They'll give you a polynomial, and you'll know the value of the coefficient. Yeah, how about this? Let me see if that's an example. Let's try this out. Here's a bonus example. Bonus example. Let's say we have a something like this. T sub 4 of x is 2 minus 3x plus 5x squared minus 4x cubed plus 7x to the fourth. Something like that. What is the value of, this would be centered at 0, of course. What is the value of f to the fourth, of 0? You actually have two ways to find that, don't you? You can actually take the fourth derivative of your Taylor polynomial, which would take a little bit of time, and plug in the 0, or you can just realize what? Hey, this is the numerator of my coefficient, okay? And the coefficient ended up being a what? A 7. So you could say, all right, 7, the simplified coefficient, had to end up being the fourth derivative at 0 over what? 4 factorial. And now when you solve, you get the fourth derivative at 0 to equal 7 times 4 factorial, which is the same thing you would get if you kept doing the power rule over and over to get to the fourth derivative. You're just like exterminating each of those terms that are smaller as you go. So it's a time saver. So you can imagine if they gave you like a 20th power polynomial and they ask you what the 20th derivative is. You don't want to have to take the derivative that many times. So you set it up like this and you solve it as an equation, okay? That's a very typical type of question that they ask. And guess what most people forget? If you're looking at answer choices, of course, answer choice A might be this correct answer, but guess what another answer choice for sure is going to be? Just 7. Excellent. For the person who forgets that the coefficients of the Taylor form have n factorial in the bottom, okay? The derivatives are just the numerators. Get it? Got it good? All right, sweet. Let's move on then. Sometimes we can create Mach polynomials to approximate functions without having to derive them using Taylor's theorem. Taylor's theorem is doing all this work right here, okay, which works for any differentiable function, by modifying existing polynomials. Okay, sweet. List the first 4 non-zero terms of the Mach-Daddy polynomials for sine of x, cosine of x, and e to the x, and then find the Maclaurin polynomials. Okay, I'm not going to derive them all for you because we've kind of derived 2 of the 3 already. So here's what I'm going to do. I will say list the first 4 non-zero terms. Okay, so instead of giving you the degree, we'll say then, let's start with sine of x. So sine of x is going to be approximated by, y'all remember what they were? It's an odd function. That helps you remember. So we start with x to the first, which is an odd term, and then they alternate. So then minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Those are the first 4 non-zero terms. So the pattern would continue. So memorize that. Have we generated cosine yet? I don't think so. But rather than generate it with Taylor's rule, how can we get to cosine from sine? Take a left. Take a, starts with D, not Dallas, not divorce. Take the, of what sign? Derivative. Thank you. There you go. The derivative of sine is cosine, ain't it? Ain't it? Yeah. So let's take the derivative of both sides of this thingamajigger-mabobber. Yeah? The derivative of the left is cosine. Squiggles. What's the derivative of x? 1. Sweet. Minus x cubed becomes 3x squared over 3 factorial. Plus the next one becomes 5x to the 4th over 5 factorial. Sorry. Getting ahead of myself. Minus 7x to the 6th over 7 factorial. Now let's simplify that. What is 3 over 3 factorial? It's 2 factorial, right? Just kind of like we do with n plus 1 and n factorial. 3 factorial is 3 times 2 factorial. So the 3's divide out, leaving you 2 factorial. Plus, what's 5 over 5 factorial? 4 factorial, because 5 factorial is 5 times 4 factorial. So your 5's divide out. So you get x to the 4th over 4 factorial. And then what is 7 over 7 factorial? 6 factorial. Pretty crazy cool. There is, so this one you don't have to memorize. This is the one you want to memorize. Is cosine even, odd, or neither, symmetry-wise? It's even, right? It has y-axis symmetry. What is the polynomial, even, odd, or neither? It's even. It has all the even powers. You're starting with 1, though. You're starting with 1 because that's the cosine value at 0, right? Cosine of 0 is 1. Remember, these have the exact same value at the center. So this is how you remember cosine. It alternates just like sine. It starts with 1, and now because cosine is an even function, you have even powers. So it's really x to the even power over that same number factorial. And the pattern would continue if you needed more terms. Like what would the next term be? Plus x to the 8 over 8 factorial. And then the next one? Minus x to the 10 over 10 factorial. Good. So you got sine. Cosine kind of comes for free. You memorized those. All right? E to the x we just developed. It's approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial. There's the first 4 non-zero terms. The next one would be x to the 4th over 4 factorial. So that's it. That's an easy one to remember. E for easy. E is for easy. Euler was a genius, having his parents name him Euler and naming the number after himself with an E. Because E is for easy. It's an easy derivative, it's an easy antiderivative, and it's an easy polynomial to generate. 1 plus x plus. Now it is the same pattern. It is x to the 0 over 0 factorial, which is 1. X to the first over 1 factorial, which is x. And then the pattern kicks up. So the pattern always kicks up on degree 2. All right? So the last one that you have to memorize is 1 over 1 minus x. And I'm going to wait to give that to you. There's a whole section on 1 over 1 minus x. Natural log of x centered at 1. If you wanted to, if I have room for one more, you might tell yourself. Memorize the natural log of x centered at 1. It shows up. We've already seen it today. I didn't distill the product, but you don't have to know that because it's easy enough to generate if you need it. But these three show up often enough, you want to memorize them, okay? So memorize these. You got to memorize? Yeah. All right, good. So in the next section, we're going to memorize the nth term for those as well in terms of n, all right? So now, here's the deal. You can modify existing Taylor polynomials to create new ones without having to generate it. So if I want to know what g of x equals sine of 2x is equal to, instead of going through the whole process of doing Taylor's theorem and generating the numerators of the coefficients, I can just modify my sine function by replacing x with what? 2x. And all that does to the graph, anytime you replace x with 2x, it compresses it by a factor of 2. You compress the sine function, let's just compress the polynomial that represents it. How about that? So here we go. G of x, or I'll just say sine of 2x, is what? Squiggles or equals to? Squiggles. I don't need the calculator in the background now. And then I'm just going to go through here, and everywhere I have an x, I'm going to replace it with a 2x. So I'm going to get a 2x over 1. I'll put it over 1, so there we go. And then minus 2x cubed over 3 factorial plus 2x to the 5th over 5 factorial. And one more, because we have 4 non-zero terms, plus negative 2x, or minus 2x to the 7th over 7 factorial. And there it is. You're technically done, right? But if you wanted to simplify this a little bit, that's going to be a 2x minus 8x cubed over 3 factorial plus 32x to the 5th over 5 factorial minus 128, I believe, x to the 7th over 7 factorial. And there's the polynomial for sine of 2x. Pretty easy. It's a big time saver. Big time saver. All right. Letter B. What else can we do besides substitute in there? What else can we do? Well, we can modify them. Like if you have a function x times cosine of x. No problem. You're just going to multiply your cosine function by x. You're going to do the same thing with the polynomial. So let's go ahead and write out cosine of x. It's worth doing again. It's approximated by, what does cosine start with? 1. Okay, and the next number is 2, right? No, minus x to the 2th power, if you will, over 2 factorial, plus x to the 4th over 4 factorial, minus x to the 6th over 6 factorial. So this is how I would recommend it. If you have to generate a new function, go ahead and write out the original one and then build it. Build it as you go. So now I'm going to multiply both sides of this by x. So I get x times cosine of x, squiggles. And now if I multiply the right side by x, all I got to do is distribute it. Yep. So you get x minus, and now it's x cubed over 2 factorial, plus x to the 5th over 4 factorial, minus x to the 7th over 6 factorial. And that is the now polynomial for this brand new function called x cosine of x. Fantastic. That's the last one I had. Oh, I got another one. Like that bonus Easter egg you find next week. All right. Okay. Comments, questions on that one? All right, how about letter C? 4e to the x squared power. Man, if I had to generate that using Taylor's theorem, I'd be happy because it's possible, but it would be a little bit labor intensive. Can I modify an existing one? Yeah. So let's go ahead and start with what? Sine of x? E to the x. Keen eye there, Gorell. Let's start with e to the x. It is approximated by 1. What's next? X squared over 2. Plus x squared over 2? I think you missed a term. Sorry. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. There you go. Okay. And I put an approximation sign right there, right? What we're going to do in the next section, just to kind of give you a heads up, we're going to put an equal sign there, but then we're going to put what at the end? Plus dot, dot, dot. Which means it goes on forever. Because as I mentioned with sine of x, if you had infinitely many terms, it becomes the graph of sine of x. It becomes the graph of cosine of x. And it actually becomes the graph of e to the x. It's pretty fantastic. But not all functions have series that approximate them perfectly when you add infinitely many terms, right? For instance, natural log of x can't do that because it doesn't have a domain of all real numbers. Okay? We call that the interval of convergence. That's coming up soon. For what values of x are the polynomials equal to e to the x for infinitely many terms? Okay, but that's looking forward. Right now, do you want to multiply by 4 first or replace x with x squared? Yeah, let's do that. So we'll replace x with x squared. So I get e to the x squared. So this becomes 1 plus x squared plus x squared squared is x to the 4th, and then x squared cubed is x to the 5th. So it's very important there. We're not multiplying through by x squared. We're replacing. If we were multiplying through, then that would be x squared times x cubed, which would be x to the 5th. It's x squared cubed, which is actually x to the what? 6. Very good. Very good. So you got to be careful. And now I'll go ahead and multiply everything through by 4. So 4e to the x squared becomes 4. Oops, I'm using equal signs. Bad me. Bad me. They should be what? Squiggles. Because we're still approximating. So distribute a 4 and you get plus 4x squared plus 4x to the 4th over 2 factorial plus 4x to the 6 over 3 factorial. And you can actually simplify that if you want. 2 factorial is 2. So if you wanted to simplify, because you were going to use this one a lot, 4 over 2 factorial becomes 2x to the 4th. The next one is 4, 3 factorial is 6, so 4 6 would be 2/3, blah, blah, blah. So they take on inherent looks of their own. But keeping it the way we did kind of preserves the pattern. All right? So there you go. We can make replacements. We can substitute in. And we can also multiply by something to get brand new functions. Now, let's see if it works. I'm kind of curious. We got a little bit of time before we take a stand. Let's go ahead and graph both of these and see how close they are. You can just kind of watch here. So get rid of that filthy stuff. X cosine of x. Let's see what that fellow looks like first. Zoom 6. Ooh, pretty cool, pretty crazy, pretty wild, pretty cool. All right, let's go ahead then and graph the 7th degree polynomial. It was x minus x cubed divided by 2 plus x to the 5th divided by 4 factorial. I'm an idiot. La, 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 la. Sorry, y'all have already checked out. I get it. I understand. I wouldn't hang around and wait for me to do it right either. Alpha window 9. I like that. By the way, it was pointed out in 4th period that some of y'all's calculus that you used for me, the alpha window 9 is not there. Yeah, so let's review the other way y'all get that. You have to hit math. Click to, y'all's probably says PRB instead of PROB. Yeah, there's some, it doesn't have fraction. So for y'all, you just hit math and you click to the left once. It's pretty nice. I did that several times. I clicked to the left once and I kept getting fraction for it because I'm used to using the old ones. This one's heavily updated, heavily. But math, probability 4. That's how y'all can do it. So I'll do it that way from now on. But it's nice if you have a really new one with the color screen, whether it's your first or second edition version of it, Tyler. it probably has that new stuff. So 6 and then math, probability 4. Does that look good? There should be a minus somewhere. The very first plus sign I type should be a minus. Good eye, good eye. I didn't put factorial on the 2, that's okay. Everything else looks good. So this should now be a red curve that kind of wraps around the blue one in the vicinity of 0. Oh, yeah. Pretty good, yeah, pretty good. So the idea behind what I was mentioning, the interval or radius of convergence for infinite series, you can kind of see it here. Again, there is a radius on either side that we can comfortably drift left and right of to use red values as approximation of blue values. And then at some point when we go past that, the values are crazy different, right? So it doesn't even make sense to do that. All right, so we are done with this section. We'll make this one due Monday. Yeah, okay? We'll make this one due Monday. But we are in crunch time, and we are at the point where everything that we cover is critically important, okay? Because there will be lots of test questions on the AP exam from this type of stuff, which is why I always do it at the end, and we're kind of going slowly through it. Make sure you understand it as we go. Make sure you practice as we go, and you'll be fine. You'll be fine. You'll be excited and happy when you see this stuff on the AP exam, okay? That's all I got. Happy National